All right, good evening. It is June 18th, and this is literally the very next day, as promised. I think I promised this anyway. After preparing the TEM Titanate lamella with the DB235, I have it loaded up here, and we're going to check it out in the Themis and see what we have. Okay, so this is obviously just a super low magged out image. I did already just take a cursory glance at it. What you're seeing here, these are bend contours, and this happens when your sample, funny enough, strangely enough, bends. It's not necessarily a bad thing, right? Because usually this happens when your sample gets really thin. Up here, this is the protective conductive coating, and then this is the SEM PT, and then this is the FIB PT. So you can see we accomplished the goal, just leaving a little bit of platinum on there. In fact, we probably could have gone even a little bit further with the final thinning, left just a little bit less on there, but that's fine. You can always remove more, but you can't remove or put material back. So we're going to take some images here. So I'm going to go ahead here and really quickly just go through the alignments here. We'll just take some TEM images. I'm not gonna do some stem here. Just wanted to show you how this looks. Should be able to get a pretty good idea of quality just from this alone. Okay, so we align the monochromator. Okay, C2 looks good. Okay, let's see how we look here in terms of C2, C3 alignment. Yeah, that looks decent, so I'm not even gonna, well, I guess I could bother with it. All right, we'll go ahead and tweak that. Why not? All right, looks reasonable. Okay, and then we'll mag up here a little higher to do the pivot points. We'll take some high-res images. I did have the sample. It's been sitting in here for a while, so it should be nice and stable. And then we can, I'm using the stage Z to minimize the image shift underneath. And then the last thing is the rotation center, which should be pretty good here still. Yeah, that's basically fine. All right. So now, I already have this tilted. You can actually see based on the bend contours here, right? If you follow the bend contours, these will lead you to like the zone axis. So we're pretty close to the zone axis right in here, right here at the interface with this film. So that's where we're going to want to take our high-res images, and we're going to want to obviously kind of center that area when we, take images otherwise. I can go ahead and put in an objective aperture. We'll go into diffraction mode. Turn off high resolution mode here. find my apertures panel. Okay. So I know like based on what C sub S should be for this microscope, the 40's good to use, but I'm actually going to go one bigger here just because we can get a little bit more detail in the high-res image that way. Okay, and that looks good. Of course, just to start with, we'll be at low enough mag that's not technically high-res to begin with. All right, so let's start with that. And we'll switch to, let me do this here, oops. Yeah, okay, so there's too much tilt for that, so yeah, don't worry. I was gonna fine tune the height, but that's okay. All right, we'll go to acquisition here. Okay, now one of the things you can do with the SATA camera here is you can do rotation, but you want to make sure if you have this crop to power 2 and you rotate, what's going to happen is it's going to crop the image to the largest possible power 2 dimension. But you see in this case, right, this ended up, we only tilted or rotated, I should say, what is that? You know, that's less than 6 degrees, but we really lost a lot of the field of view. We went down to 512 by 512. So if you deselect that, right, you can see, you know, we went from 1024 to just 529, okay? So a little bit of a benefit there. All right, so I'm gonna take a few of these. I'm gonna start by having the this interface centered, and then if we do, I have this set for 2 seconds. That should be okay. Okay, and it's a little bit saturated, so what I'm going to do instead is I'll do 4 frames. Okay, that's much better. Not quite clipping the signal as badly. I'm going to move the lamella up here. So notice like the sidewall looks nice and smooth, right? We're not seeing really any rippling, really not much in the way of curtaining, which is, you know, what we hope for. Okay. Oops. I'm going to increase the mag here. We'll take some images at different mags. Okay, we can probably get rid of that now. Okay. Let me put the interface right at the middle, and we'll take another picture. Yeah, come on. Come on. All right, there we go. You don't have to take your jump this way, of course. I'm just doing this here. we got a nice smooth sidewall. Come on. All right, let me switch to the piezo move since this is being a pain. Okay, sometimes you might need to, I mean, that looks straight, so I'm not going to adjust it. Well, there might be a little bit, I mean, in principle, this should be rotation free, but you might need to make like a little tweak here and there. Yeah, so that's a little bit of a tweak. I made a little adjustment with the stage Z. Okay. Go back and take a look at some of these. Yeah, looks good. All right, so let's mag in on the surface here. We'll take some high-res images of that, and we'll see how that looks. So I'm going to go all the way up to 380K indicated, and then I'm going to back out from there because actually it's going to be easier to like fine-tune the focus at this setting. Do piezo move Z. All right, then we'll go to position, and there we go. So nice looking high-res image. Stigmatism, objective astigmatism or stigmation looks good. Okay, let's see if this is stable enough for 2-second exposure. Yeah. So we're seeing these spots out here. These are like 100 picometer detail, so looks nice. Take a few of these actually. Beautiful. All right, let's go down a mag click. Okay, I mean, in principle, you shouldn't, I mean, in practice, you know, there can be a little bit of a change in your focal state when you change mags. It shouldn't be like dramatic, but it can still happen. So you always want to, you know, tweak it each time, especially at the higher mags, like with atomic level detail. Looks good. I'm not doing frame integration because I don't need to, right? It's stable enough as it is, so go down one more click. Okay, that looks good. Let me adjust this piezo move Y. So it looks like our handiwork was pretty good. Yep, nice looking image. Yep, this was our first one. It was a slightly, basically the same defocus, really not any different. It says minus 21. That's minus 20, so I don't know if you're going to really tell the difference with 1 nanometer of defocus, although it may not even be that. It may be the actual value may be a little bit different. There's a way actually we can measure it. This is actually a video I've got in the works. Is how to measure your defocus. So, and there is a way to do it. Yeah, see that looks still. I mean, at this point, it's tough to tell with your, with the FFT because we can't see a wide field of view. So at this point, we're just, because since we did it at higher mag, focused at higher mag, we're just going to trust that it looks good here. Yeah, basically still does. Okay. All right, we'll take one more at 1 mag click lower. This is kind of the threshold where we can see atomic level detail. Okay. And we really can't make heads or tails of that. I mean, we're seeing some aliasing here, it looks like. One thing I am going to do is I am going to take some images of the, so we're definitely seeing some aliasing there. I want to take some images at high mag of just the amorphous film, and I'll explain to you why. So I'm going to turn off the rotation because we don't really care for that. But we'll go up here all the way to 380. Spread the beam out. Okay, we'll move piezo, move down, so we're just basically over the film. Okay, so our astigmatism looks good. Now what I'm going to do is I'm going to intentionally defocus this so we can see a bunch of rings. So we can see several rings there. And it's telling us we're negative 250 here under focus. If we go back the other way, yes, we can see the rings, but it's a little, it's not really any more obvious. This can be a little tricky to do. In order to do this measurement properly, it might be because we need something a little bit lower Z. If there's only like 3 rings in the FFT, and of course we can denoise this and do like a rotational average, which you absolutely should. But it gets a little tough to do. This might be easier to do with something like a lower Z material. Because I was hoping to be able to see more rings, but then again, this is scattering to a higher angle or more strongly, so I kind of would expect it to be able to see a little bit more detail there, so that's kind of interesting. But anyways, it looks good otherwise. Well, here, I'll go ahead and just take this. Okay, show the spatial frequency. 400. Yeah, so I mean, it looks good. You do need a big enough objective aperture to see that, but I mean, that looks by and large. I mean, I didn't even tweak the objective stigmators. I mean, it looks pretty good there. So Okay, so that was the video I wanted to share with you. Just, doing a cursory examination of the lamella that I made yesterday with the Helios Nanolab 600i. So I hope you found that useful. I am going to record another video here after this, actually talking about measuring your objective aperture angles. So hopefully you'll stick around for that. All right, so let me go ahead here and stop this video, and then I'll start recording another one.